These programs are distributed under a Creative Commons Attribution, Non-Commercial, No Derivatives license. You may copy and distribute these programs free of charge. You may not sell them, and you may not alter them. These programs are part of a study examining the utility of podcasting as a means of medical education. If this is the first time you are watching a podcast in this optics series, send an email to jyoungmd@gmail.com with your name, position, institution, and city, state or province, and country. Thanks, and enjoy the podcasts. This is probably my favorite lecture in the entire optics lecture series, and it is a discussion about vergence. In optics, there are often multiple ways to approach problems. And I'm going to tell you now that there are two tools in optics that are so powerful that if you have the opportunity to use them, you should use them to the exclusion of other ways to approach problems. And the two tools are vergence and power crosses. We're going to be dealing with power crosses later on in the series. We're going to deal with vergence now. Now, you're going to read in textbooks or hear in other lectures that vergence is a description of the shape of a wavefront of light coming off from an object. I don't want you to think in those sorts of terms. I'm going to present this in a very sort of problem-solving oriented way. I want you to think of vergence as a description of where, from a particular point, the rays of light converge. So in the sample that I've shown here, we're starting out with an object that we traditionally choose as a candle. And we're going to talk about what the vergence is at a few points from the candle. Vergence as an absolute value, it tells us where the rays of light converge, and the relationship is 1 over the vergence value is equal to the distance in meters to where the rays of light converge. So if I ask what is the vergence at 1 meter from the candle, what is the vergence over here? The answer is the absolute value of the vergence is 1, because 1 over 1 is equal to 1 meter. The vergence over here, let's say that this point is half of a meter, is going to be 2, the absolute value of the vergence, because 2 tells us that the rays of light converge half a meter. 1 over 2 is equal to 1/2, so we're half of a meter from where the rays of light converge. Now, the other thing that we have to know about vergence is the sign. By convention, we're going to look at problems where the rays of light start out on the left side of the page or the left side of the screen and propagate to the right side. And this convention is so important for us that I'm going to ask you, if you're given a problem where the rays of light are moving in any direction anywhere else, to rotate the page, to rotate the piece of paper until the rays of light are moving from the left side of the page to the right side of the page. Okay, so once we have that convention, the sign indicates whether the rays of light are converging to the right or to the left of the particular point that we are choosing. So once more, if I am looking 1 meter from the candle, right over here, and we're saying that the absolute value of the vergence at this point is 1, because 1 over the distance to where the rays of light converge is equal to 1. The rays of light are converging to the left. Left of our area means a minus vergence. So the vergence here is -1. The vergence here is -2. A minus also means that the rays of light are diverging. But I want you to think of these more concrete terms of where the rays of light converge. And if they converge to the left, it's minus. And if they converge to the right, it's plus. Now I can give you any problem. I don't even need a diagram for it. If I tell you the rays of light are converging 1/4 of a meter to the right from where we are, and I'm asking from where we are what is the vergence, 1/4 of a meter means that the absolute value of the vergence is 4, right? Because the absolute value of the vergence is 1 over the distance in meters to where the rays of light converge. I'm telling you they converge 1/4 meter to the right. Therefore, the inverse of that is 4. So the absolute value is 4. The rays of light converge to the right. To the right means plus. Therefore, the vergence from the particular point that I'm describing must be plus 4. Okay, let's do some practical problems here. Right, so this is what I showed you. 1/2 of a meter, the vergence is equal to -2. 1 meter, the vergence is equal to -1. Okay, so let's do these problems. What is the vergence at point A? Well, we are 1/4 meter from the candle, 1/4 meter to where the rays of light converge. 1/4 meter means that the absolute vergence, the absolute value of the vergence is 4, and the rays of light converge to the left, so A must be -4. C must be -4/3, -1.33. What do you think the vergence is at the candle, at the flame? Well, I said that the absolute value of the vergence is 1 over the distance in meters to where the rays of light converge. So if we start out where the rays of light converge, the distance to that point must be 0. The inverse of that is infinity. So the rays of light at the candle's flame have a vergence of infinity. They don't have a vergence of 0. What does a vergence of 0 mean? A vergence of 0 means that the rays of light converge at infinity. So the rays of light are parallel when the vergence is equal to 0. Rays of light coming from the moon have a 0 vergence. You're going to say, well, Dr. Young, they don't have a 0 vergence because the moon is some discrete distance from us. Well, yeah, I don't know what the distance is. It's very, very far. It's effectively an infinite distance. So I'm going to represent to you that the rays of light coming from the moon have a 0 vergence. Okay, and these are the answers to the previous question. Okay, here's one that's kind of tricky. And it is the sort of problem that you might see on an exam. And I'm going to ask you what the vergence is at this point here. Okay? At this -10 centimeter point. Well, I'll tell you what the vergence isn't. Okay? The vergence is not -10. It's not, well, 10 centimeters is equal to 0.1 meters, therefore it must be -10. No. If you look carefully at the baseline of this diagram, the distances are not given with respect to the object. They're not given with respect to where the rays of light converge. The distances are given with respect to the lens. For us, the lens is not an important landmark in determining what the vergence is. So the first thing that we want to do on a problem like this is to renumber the baseline so that it gives us distances not to the lens, which again is not important, but distances to where the points of convergence are. So I've redrawn our base here. And now the same point, this point which was -10 centimeters from the lens, is correctly marked as being -40 centimeters from the point of convergence. Now, if we were really being orthodox, we wouldn't even want to say centimeters. We would say this is -0.4 meters, or 0.4 meters from the point of convergence. So if I ask you what the vergence is here, it's certainly not -10. That's obvious now. What is the vergence at this point here? Well, when you're asked what the vergence is, you reply with a question. And the question is, where do the rays of light converge? So from our point of interest, the rays of light converge 40 centimeters, 0.4 meters to the left. So the absolute value of the vergence must be 1 over 0.4, or 2.5. And then the next question is, are the rays of light converging to the left or to the right of where I am right now? And the answer is that they're converging to the left. So the vergence at this point must be -2.5. Similarly, the vergence here is equal to -5. And the vergence of the rays of light immediately before striking the lens is equal to -2. Now, what is the vergence of the rays of light immediately upon exiting the lens? Well, on exiting the lens, we see that the rays of light are now converging at this point over here. They're converging at the image. And I know I've drawn the image upside down, and indeed it is, but we're only going to learn much later in this course why the image is represented upside down. For the time being, trust me. So we are 0.75 meters from where the rays of light converge. At this point, the absolute value of the vergence is 1.33, right? This is 3/4 of a meter. 1 over that is 4/3. So the vergence is 1.33. And where do the rays of light converge from our reference point here? They converge to the right. So the value of the vergence here must be plus 1.33. So here's the question. The vergence coming into the lens is -2, and exiting the lens is plus 1.33. So how much vergence is contributed by the lens? Or rephrased, what is the dioptric power of the lens, since that's going to give us the same value? Well, whatever it is, when you add it to -2, you need to wind up with plus 1.33. So what number added to -2 equals plus 1.33? The value, the dioptric power of the lens, must be plus 3.33. This is often represented in a formula that is really kind of more of a concept than a formula. The math here is not particularly difficult, where V, the vergence exiting the lens, is equal to U, the vergence entering the lens, plus D, the dioptric power of the lens, meaning that you can add the dioptric power of a lens to the incoming vergence to arrive at the outgoing vergence. Now, if I hadn't even drawn this whole right-hand side of the diagram, if I had merely told you that the vergence at this point, the point exiting the lens, is equal to plus 1.33, and asked you, well, where do the rays of light converge? The answer is that they converge 1 over 1.33 meters, or 3/4 of a meter, and plus means to the right. So you didn't even really need this whole second half of the diagram here. There are 4 sorts of questions that you can be asked in lens object image problems. They are, what is the power of the lens or location of the image and object? And that's all kind of one question. That's all sort of one thing. We just solved that with the previous problem. We found out what the power of the lens is. In this problem here, we're going to find out what the distance to an image is. But so one question of the 4 that you can potentially be asked is, what is the power of the lens or location of the object or image? The second question that you can be asked is the image or object real or virtual? And we're going to be dealing with that very shortly. The third question is the image inverted or upright? We're going to be dealing with that later on. And the fourth question is, what is the relative size of the image to the object? That's magnification. We're going to be dealing with that later on too. So of those 4 questions, 2 of them can be answered with vergence problems, using vergence. One of them is the powers of the lens and distances to the image object, and the second one is real and virtual. Okay, so in the previous problem, we solved for the power of a lens. Now let's solve for the distance to an image. What I need to know to figure out the distance from the lens to the point of convergence, because the point of convergence represents the image, what I need to know to figure out this distance is, of course, the vergence of the rays of light exiting this lens. The vergence of the lens at this point are going to tell me where this point is. So exiting vergence is equal to entering vergence plus dioptric power of the lens. What is our entering vergence? Well, it's the vergence of the rays of light immediately before striking the lens. So when I ask you, what is the vergence at a particular point, you answer with a question. And the question is, from that point, where do the rays of light converge? So for rays of light entering this lens, they converge 10 centimeters to the left. Now, I said once we finished with prisms, we're no longer going to deal with centimeters, we're only going to deal with meters, so let's convert this in our head. The rays of light converge 0.1 meters to the left. Vergence is equal to, the absolute value of the vergence is equal to 1 over that distance in meters. So 0.1 meters means that the vergence entering the lens must be 10. The absolute value of the vergence of the rays of light entering this lens must be 10. The next question is it minus 10 or plus 10? Well, the rays of light are converging to the left, therefore it must be minus 10. So the rays of light entering this lens have a vergence of minus 10, U. D is given as plus 15. V, the exiting rays of light, the vergence of the exiting rays of light, is minus 10 plus 15, which is equal to plus 5. So at this point, exiting the lens, the rays of light have a vergence of plus 5. With your eyes closed, plus 5 always means the same thing. It means that the rays of light converge. 5 means 1/5 of a meter, and plus means to the right. So the rays of light converge 1/5 of a meter to the right. Of course, that is the answer to this question. It is 0.2 meters, or in centimeters, 20 centimeters. This is an example of a vergence problem where both the object and the image are on the same side of the lens. So let's solve this problem with this candle here as our object. So this candle is how far from the lens? 10 centimeters plus 10 centimeters, 20 centimeters. So this candle is 0.2 meters from this lens. 0.2 meters means that the vergence, the absolute value, is 1 over 0.2, which is equal to 5. And the rays of light converge to the left. So the vergence of those rays of light entering the lens must be minus 5. If we take the second smaller candle as the image, then the rays of light that form the image are converging 1/10 of a meter to the left. Now, in truth, I should have drawn these lines converging on the image as dotted. And there's a reason that will be evident in a couple seconds why I didn't. But have them dotted. Meaning that we understand that it's not really that the light is striking this lens and bouncing off. It's not a mirror. What's happening is that the rays of light from the object are hitting the lens and are diverging even more widely, so that if we extrapolate them backwards, they converge to this point here. So we have a vergence of minus 5 going into the lens, a vergence of minus 10 coming out of the lens. What must the dioptric power of this lens be? And the answer is that it must be minus 5, right? Minus 5 going in, minus 10 coming out means that the dioptric power contributed by the lens, the amount of vergence contributed by the lens, must be minus 5. Minus 5 plus minus 5 is equal to minus 10. Now, let's take a completely different problem, but with the same lens. And in this case, we're going to take this smaller candle here as our object, and this larger candle further back is our image. Now when I say, what is the vergence of the rays of light striking this lens? The answer is that the vergence of the rays of light, well, where do the rays of light converge? They converge 1/10 of a meter to the left. 1/10 of a meter means that the absolute value of the vergence is 10. To the left means that the sign is minus. So the rays of light entering this lens must have a vergence of minus 10. What about the rays of light exiting this lens? Well, of course, what's going to happen is that the rays of light strike this lens and exit the lens diverging, and we're going to extrapolate it backwards to this point here. So the rays of light exiting this lens must have a vergence of minus 5. So it was minus 10 going in and minus 5 coming out. This lens must have a dioptric power of plus 5. So what I want you to take from this is that plus lenses in and of themselves do not mean that the image needs to be on the right side of the lens. Sometimes the image is on the left side of the lens. Even though a plus lens is a converging lens, in this case it is insufficient converging power to force the rays of light to converge on the right side. they emerge from the lens diverging, but diverging less than they would have been had the lens not been there. The other thing that we're going to see later on is that this is how a magnifying glass works. A magnifying glass is a plus lens that we use to magnify when it has insufficient converging power to force the rays of light to converge on its right side. But we'll see that later on when we deal with simple magnifiers. Okay, so depending upon which of these we take as the object and which we take as the image, we can come up with the result for the dioptric power of the lens as either being -5 in the case of this as an object, or +5 in the case where we took this one as an object. And that's why I didn't draw dotted lines, because I wanted to use this diagram for both examples. Okay, this is a concept that is extremely simple, and yet I've heard explanations for it that are very complicated, where people say a real image is one that can be projected, except in this case, except in that case. I'm going to give you a rule without exception, and that is, as long as we follow our convention with rays of light moving from the left side of the page to the right side of the page, that the order of the object and the lens and the image should be object, lens, image. If one of those things, the object or the image, are offsides, they are virtual. So if an object is to the left of the lens, it is real. If an image is to the right of a lens, it is real. If an object is to the right of a lens, if it's offsides, then it's virtual. And if an image is to the left of the lens, it is virtual. And that is an inviolate rule. Oh, so on this previous slide, we have a real object and a real image. In this slide here, we have a real object and a virtual image, because that image is to the left side of the lens. Can there be virtual objects? There sure can be. And we'll see that when we do multiple lens problems.